Anyways,
10 in the morning. Now we're seeing it.
you're seeing the right
That's
thing.
okay, that's good.
Okay, all right, there you go.
Now Paul is asleep.
No, that's-
Again, this is more foreplay than I'm used to. Lovely.
Okay, so we're really delighted this morning to have Paul Canfield, who's visiting us from Iowa, from the University of Iowa State University, and he's going to tell us about new materials physics. Thank you, Paul. And it's 1 hour and 20 minutes, and if you can make sure you finish 10 minutes before the end, so we have time for questions.
I'm going to do it differently, Piers. Interrupt me during the talk. I want to have it interactive and it will last as long as it lasts.
Very good.
Very good. And for students, can I see a show of hands of students? I can. Yay. I want you to ask questions. No. I want you to ask questions and I'm going to incentivize it because I brought party favors for everyone who asks a question. That's right. What?
We ask a question.
I-
It's not
until-
gross, though. Important.
Pardon?
Is it crust gross?
It's 2 examples of fritted crucible sets. Right. And the last part of the talk will go over that anyway. Let me get this out of the way. Oh, isn't that lovely? I usually have a warm-up, eat, wear, and kill, but that is if we start early and we have started late. If you want to play eat, wear, and kill, we'll do that later. Okay, so new materials physics. Yay. All right. Let's say one morning your thesis advisor, okay, that guy during one of his rare visits to the lab says, in order to graduate, you need to work in the new field of quantum materials. And you ask yourself, oh, yes, thou shalt. And you end up asking yourself, what is the future of quantum materials? Okay. I can't believe this has turned 50. I'm still treating this as a contemporary movie. Yes. So how shall we start thinking about quantum materials? Well, how do we start thinking about the future? We can see what intelligent people have said about the future. I never think about the future. It comes soon enough, says Albert. It's hard to make predictions, especially about the future, says Robert. If an elderly, distinguished scientist says something is possible, he's almost certainly right. If he says it's impossible, he's very probably wrong, says Arthur. The best way to predict the future is to invent it, says Theodore. And the future is made of the same stuff as the present, says Simon. Okay, now I'm going to have my differences with Simon, and I'm going to focus on the idea that the future of quantum materials is finding and creating and even understanding different stuff. Okay, so the future is growth. Yeehaw! All new materials growth and discovery efforts are negotiations with nature. Okay, and Mother Nature, not the journal. The journal is a different type of mother. Okay, so a new growth is the intersection of an idea, the periodic table, and your experimental capabilities. This is probably the most complicated equation I will show in today's talk. Okay, so any lab has certain capabilities and lacks others. Okay, solution growth, which is what I'm going to emphasize, is very versatile and can work on many classes of materials. And what's lovely, it doesn't require a knowledge of the compound's composition or even the compound's existence. Okay, all you have to do is to be able to intersect a liquidous line or surface for primary solidification, and you can get that material even if you're way off from the stoichiometry of it. So it's lovely. If you want to be cynical, it encourages ignorance, but it's versatile and allows you more opportunities to find materials. You don't have to guess right. Okay. Now, as you engage in this negotiation, it's good to have broadly based ideas. Okay. You don't want to be dogmatic when you go into a negotiation. If you say, I demand this, that's not a negotiation, it's a demand. Okay. So, for example, you can look at the periodic table, and here's sort of an idea of for superconductivity. You can think of certain elements having high phonon frequencies when they're tightly bound, You can also change band filling. You can change band width. These are all ideas that we play around with if we're going to be trying to think of superconductors. Okay. If you're interested in magnetism, these materials will be quite devout in their trivalent local moment magnetism. These, especially in intermetallics, can have fragile magnetism, devout or non-existent magnetism, and deuterium and ytterbium also can hybridize. So you can have strong magnetism, flexible magnetism. And if you're interested in spin-orbit coupling, which, for example, for topological materials, the mapping onto the periodic table is even easier. Just head down here to the heavy side, and you tend to increase your spin-orbit coupling. Now, the idea. The idea is hard. The idea is like unicorns in the forest. You sit, you're pure, you're tranquil, and they can lay their horn on your lap. Okay, now, pure, probably not. Tranquil, generally not. But you still need to have an idea. Okay, but nature's kind. She doesn't care what your idea was, just as long as you made a growth and examined the result. Many materials are born from stupid ideas, okay? But people proceeded. So it brings me to my favorite quote from Sophocles: "Seeking you shall find, what's unsought goes undetected." If you don't make it and measure it, you'll never find it. Now, that's old and dusty. We can have a more modern version of it. Just do it. And fine. That's sort of the spirit of how we're going to approach here. So let's look at examples of negotiations. If I think of quantum materials, it's a long list, much longer than this, but you can think heavy fermions, strong spin-orbit coupling, valence fluctuations, emergent phenomena, wild Dirac, 2D, quantum phase transitions, all of those work. What I want to do in today's talk is look at some specific examples. We'll start with a very finite one on topological layered systems, then a discovery of a large family of correlated electron materials, search for fragile magnets, use promising phase spaces, and at the end, I'll go over how we can use these frigid crucibles to improve crystal growth. Okay, so that's the agenda. Let's start. So first negotiation really is an attempt, like you do with a starting class for undergrads, is how to take a word problem and turn it into simple equations to solve. You know, so you can enunciate it, but then how do you translate that into something physical, into something real? Okay, so what we wanted to do was find a low degeneracy, topologically non-trivial compound that we could readily study with ARPES. That desire takes the whole periodic table and condenses it down into two materials. Okay, let me show you how this worked. Okay, so we wanted the lowest number of symmetry operations, so we can go and say, hey, triclinic. Okay, that's going to be, you know, the least symmetric we can have. We can say we want topologically non-trivial. Let's go down to the heavy side, and we can go to the heaviest possible, almost stable element, bismuth. I'm told the half-life is slightly larger than the age of the universe, but the nuclear physicist said, no, it's not stable. Okay, I can still work with it. So I can then go to Pearson's crystallography. I can put in bismuth. I can put in triclinic, and I can say, look, let's keep it simple, 2 elements. Okay, and when I do that, I get an incredibly small number of hits. Bismuth oxides, not interested in, bismuth 2 rhodium, and then this nitride. So it basically goes to bismuth 2 rhodium. Okay, so let's look at this. Holy Moses. If you look at the crystal structure of this, you see these empty spaces. These are van der Waals gaps. Okay, so this looks promising as a layered material. Okay, let's look at the phase diagram. Yalakba. This is very promising. Okay, so we have an exposed liquidus line for the phase we want. We can come in, hit it, decant. We've gone through all the steps. We can make it. It can cleave. It can be measured. And we discovered a weakly topologically insulating state, Van Hoff singularity, in triclinic rhodium bismuth 2. My colleague Adam Kaminsky could cleave it, could study it. We could have band structure. reproducing this. So sometimes nature is kind. Okay. This is an attempt to show you how you can go from just an idea and try to narrow down all the combinatorials and end up with a material. Yes.
How does business selenite fit in?
Pardon?
How does business selenite, which is a topological insulator, how does that fit in?
Well, it didn't show up in my cascade of bismuth triclinic. So my suspicion is it's not triclinic. Okay, because I was really trying to go for the lowest possible symmetry. Okay. And could you pass on that because I'm encouraging questions? All right, very good. Other questions on this? Yes.
Where's the topological band?
I'm sorry, what?
Where's the topological band in the Ames measurement?
Oh, good question. And I don't know if I can do it. What we're seeing is this Dirac-like feature here. Okay. And again, Flora, maybe you can be the crucible fairy and help passing them out. Oh, thank you. All right. Good. Let's carry on. So let me go to a larger scale project then, okay? This was a one-off. Let me go to something else. And this is an example of having some vague and curious ideas and see where they lead to, okay? So my group has discovered and grown many types of quasicrystalline systems. We've discovered more binary stable quasicrystals than any other group in the world. We've discovered and studied many Kondo lattice systems, and arguably we've discovered probably the most ytterbium-based Kondo systems around, okay? So with this background, we ask these questions, okay? So if a crystalline unit cell gets bigger and bigger and bigger, will we start having quasi-crystal-like behavior? And the reason I ask this is if you have a quasi-crystal, if I go back to something like this, and you ask, what's the unit cell size of this? Pedantically, the unit cell size is this. It's about 2 millimeters or 1.5 millimeters. That's a big unit cell. Now, that's pedantic and that's not experimentally exact. The experimental statement is, well, it's larger than the coherent volume you probed with your X-ray beam or your neutron beam, and that's still pretty big, okay? So the reason I'm asking this question is, look, quasicrystal is an infinite-sized unit cell. If I go bigger and bigger and bigger unit cell, at the end of that walk, do I see quasicrystals ahead of me, or are they on a completely different Riemann sheet, completely different dock? Okay, so that's one question. The other question is, could we find a dilute ordered Kondo lattice? And if so, would it behave like a single ion impurity, or would it still have some sort of coherence? So we wanted to have a minimum number of Kondo-like ions in as large of a unit cell, still fully occupying a unique crystallographic site, not diluting it out and introducing disorder. Okay, so with those two questions, we could again go to Pearson's. This was back in the day when you could have Pearson's in book form, and in the back of one of these, you could find all the unit cell symmetries, and you could see the families of small, medium, and large unit cells. So I went to cubic. I went to as large as possible, threw out some rare earth bismuth 297 because I'm never going to make those. And as I started looking through it, I found this beautiful paper by one of my heroes, Wolfgang Jaitzko, a prolific solid-state chemist. Okay, and they had at that time recently found this family of rare earth transition metal to zinc 20s. Okay, this has a unit cell of 184 atoms. It has a 14 angstrom on the side unit cell dimensions, and the rare earth distance is greater than 6 angstroms. Okay, and as you can see, it's mostly zinc. And I will just assert right now, the transition metals are all non-moment bearing. Yeah, we have proof for that. That's not immediately apparent, but it's true. So you have basically 1 out of 23. Now, this requires that we figure out how to handle zinc. Zinc has a large vapor pressure. We needed to figure out what are the rules for dealing with it. But if we played eat, wear, kill, zinc is one of the benign ones. Zinc oxide is used in sunscreen. It's not going to poison you. So it's fairly benign. Now, the nice thing is once we figured out how to handle it, these things love to grow. You can get cubic centimeters or larger of these. Now, great. What now? Well, we have representation for this rare earth transition metal 2 zinc 20 for the whole iron column, the whole cobalt column. We needed to try to figure out what the basic rules were. Yaitsko had done the crystallography. He had done no physical properties. As a matter of fact, his synthetic method had some disorder. Single crystal growth got rid of that to a large extent. So we look at gadolinium. Gadolinium has no CF splitting. It has the largest de Gennes parameter, so it's going to have the highest ordering in simple models. Let's just get a measure of these series. If we look at cobalt, rhodium, and iridium, we see antiferromagnetic ordering. If we look at magnetization versus temperature, modulo 10 Kelvin, that's not unreasonable for 1 out of 23 atoms being gadolinium. Now, on the other hand, if we look at the iron column, iron, ruthenium, osmium, iron orders ferromagnetically at 90, ruthenium about 30, osmium about 10. This is a remarkably high ordering temperature for just gadolinium. Okay, and again, I'm just going to tell you there's no moment bearing on even the iron site because it's so dilute. Okay,
Can I
now,
ask one question?
please.
So if you look at this unit cell, right, so there,
Yes.
it looks like on the previous.
Yes,
slide,
Shirley.
It looks like there are plenty of positions that are almost equivalent for the gadolinium.
There's only one unique gadolinium site.
Yeah, but so why does the gadolinium not sit in some other sites and making your unit cell even larger? I mean, if you look at the site where the gadolinium sits and then.
Yes, here.
Yes, and then the
And
site
there,
on
and there.
top, yes, there is this.
Are you asking me why these elements form this crystal structure? The answer is a minimum in free energy.
Yeah, but it looks like the energy putting the gadolinium up there is only.
You're saying, is it prone to disorder? Not very much. You know, you can do the crystallography. You can also measure residual resistivity ratio. These order quite well. So you're expressing, wow, large unit cells. How did nature figure this out? That is one of the amazing things. But it is a well-defined unit cell with a single rare site that's fully occupied.
It just looks that some sites look almost equivalent for the gadolinium. So I'm just wondering why tiny.
More than one in this structure.
What?
I just don't understand.
No, nor I.
The side on top, if you just move the red dot there up to the top.
Where do you want it? Here? There's
Yeah, for example.
Well, yeah, there's a gadosite here hiding behind the zinc.
Yeah, that's.
There's a gadosite here. There's a gadosite hiding behind that zinc. There's a gadosite there. I mean, please look, it's 23 atoms, and yet the unit cell has 184. So I have multiple formula units per unit cell.
So why iron doesn't have a moment in this case?
It doesn't. I mean, in most intermetallics, especially dilute ones, thank you, Laura, especially dilute ones, transition metals tend to drop their moment. Actually getting transition metal magnetism in intermetallics takes effort, especially in the case of this. Many of the 122s, rare earth nickel 2 germanium 2, nickel's not moment bearing. Rare earth iron 2 germanium 2, the iron's not moment bearing. Okay, so that's not unusual. But we'll get back to this question in just a moment, okay? Because, you know, so why am I seeing high ferromagnetism here? Students, the old farts are getting the crucibles. Work harder. All right. So there's nothing special about gadolinium. I can look at gadolinium, terbium, dysprosium, holmium, erbium, and thulium. I see ferromagnetism. And as a matter of fact, if you plot the ferromagnetic transitions temperature versus de Gennes parameter, this is some of the best de Gennes scaling of magnetic ordering you'll see. This is what you'd anticipate from a simple model that says theta should scale as de Gennes factor mean field. You should have T Curie. And there's very little ambiguity here because it's ferromagnetic. So I'm not changing my wave vector on any of these. Now, I can look at the antiferromagnetism of gadocobalt, of terbium cobalt. That's 2. It makes a line, but the line goes through 0, 0, which is a third data point for de Gennes scaling. So you're getting ferro de Gennes scaling here. The question, of course, then is why is rare earth iron 2 zinc 20 series manifesting such high ordering temperatures? And the answer, going back to it's not moment bearing, is we are really close to the Stoner limit for yttrium or lutetium iron 2 zinc 20. And I can show you that. Okay. So the Stoner limit, by the way, for those not familiar, if you think of the elemental Olympics of ferromagnetism, you have iron, nickel, and cobalt there on the podium, and palladium, just missed third place. It's almost ferromagnetic, okay? And you can parameterize this by, if the Stoner parameter is greater than 1 or hits 1, it becomes ferromagnetic. If it's less than 1, it's close, okay? And it turns out for the yttrium iron 2 zinc 20, you're closer to the Stoner limit than palladium. You have a Stoner parameter, which you can infer from the specific heat and susceptibility of about 0.9. And what's nice is, if you look at the yttrium, I can dilute with cobalt. I see that I drop out extra electrons per formula unit. I can also substitute zinc and aluminum. And again, I get the same drop. So this is beautiful band magnetism. It's almost ferromagnetic. And in this case, what happens when you drop a rare earth into this highly polarizable matrix, it orders at a higher temperature than the others. And you can see the similar dilutions here for the gadolinium iron, cobalt, zinc 20. I can have my TC drop as I'm losing this Stoner parameter, and I can do the same thing for zinc. This I was very proud of because we can do two types of different, very different substitutions, and all of the physics maps onto this. So, yes.
Well, just curious. So the parameter Z,
Yep.
you're writing down, appears to be related to the Wilson ratio. So the theory is that if I want to compute the Stoner parameter, it's non-trivial. I have to compute the bubble system of Green's function, right? It's RPA type calculation. So here there's a simple answer that seems to come out from just the Wilson ratio.
Yeah, you have to be a little bit careful here because you have to be very, very careful. Excuse me. Really? You have to be very careful with, for example, your susceptibility, because I have to get rid of the core diamagnetism. I'm looking at a small susceptibility. And this is just an experimental detail, but as a theorist, you might worry about it too. So I can figure out what the core diamagnetism for zinc, yttrium, and iron are just by going to the noble gas filled shell before that. When you do that correction, yes, it works very nicely. Yay. All right, so to address the question about the heavy fermions, we had 6 families of rare earth T2 zinc 20, and when we got to ytterbium, it was amazing. We discovered a 6-pack of new ytterbium heavy fermions, okay? Because each of these ytterbium compounds have heavy fermion-like behavior. Here's a generalized Katawaki-Woods plot, and I'll show you some data supporting this in a moment, where I can plot A versus gamma, and here are the 6. And what's nice is all of these are isostructural. Changing the transition metal doesn't change the CF environment of the ytterbium because nearest and next nearest neighbors are all zinc, okay, as here. So this is when I finally started believing this generalized Katawaki-Woods, because before that, all of these different compounds are different structures, different ligands, everything. Now, let me show you some of the data.
Can you define A for those who've never seen it before?
Surely. Give me 2 slides. So if I look at the magnetization versus temperature, I can see my loss of local moment behavior. Cobalt is on a different slide. It has a very different condo temperature. Okay, I can look at C over T versus T squared, giving me my gammas. I have gammas between 500 and 800. And to get to Pierce's question, if I look at my resistivities versus temperature, I plot resistivity versus T squared. A is the coefficient of the T squared resistivity. Okay. So you take those and you can actually create these. I would be saying that ytterbium iron 2 zinc 20, I'm hybridizing my full R log 8. And what's nice is I could parameterize that. Excuse me, where's my slide? Nope. Okay, it's in backups. I can do Kopler-Schrieffer analysis of the susceptibility and the specific heat, and I can, by doing a more detailed analysis, indeed convince myself that I have my R log 8 here in agreement with what I'm seeing on this generalized Katawaki-Woods. So for these materials, I can hybridize R log 4, R log 8 entropy away, and I have a selection of condo temperatures, 1.5 for the cobalt, reaching up to about 33 for the iron. So this is a beautiful family for looking at ytterbium heavy fermion behavior. My frustration is my ARPES colleague has been unable to do the ARPES on these. Ytterbium's a beautiful ARPES because it doesn't cleave. It's a large unit cell cubic. So this is one of my frustrations. Otherwise, we've done a lot of fun work. Laura.
Did I miss the way? Did you show resistivity or do you have?
Yes, I did. Here's the resistivity.
Okay, great. Thank you.
Here's on a bare plot. Here's the T squared. And the cobalt is such a low condo temperature. It's a separate
Thank you.
collection of data.
So how you define N?
Two ways. One is off of the generalized Katawaki wood, but and this is not my computer, so I don't know how to move around. In backups, if you want me to try to scroll down quickly, I can also look at the susceptibility and specific heat and do a Copeland-Schrieffer analysis of them, and that allows you to see that the curve is fitting for the R log 8 in this case too.
So what do you take N as being physically?
Oh, okay. So for a doublet cerium,
Yeah.
your gamma TK is R log 2.
Yeah.
It's the amount of entropy you're hybridizing away. Here, it would be R log 8. So I'm actually having my full Hund's rule ground state multiplet being hybridized away. If you want to think of it, what I'm doing here is I'm not changing my CEF splitting of the ytterbium much, but I'm changing my condo temperature. Okay, with a high enough condo temperature, I'm able to have it hybridize my full R log 8 before I've depleted some of my entropy by going through CF splitting levels.
Right, so if you did crystal field measurements,
You'd
you'd be able to deduce your N value from those. Is that a statement?
Well, no, because it's your CF splitting compared to your condo temperature. I mean, think of most cerium compounds. You're probably used to R log 2 as the entropy you're hybridizing away. That implies you pass through CEF levels before the condo temperature kicks in and hybridizes your last.
Yeah. So it's the number of your degeneracy at your condo.
Correct.
Is your N.
Yes.
Well, is it surprising that crystal fields are so low? I'm used to seeing ytterbium crystal fields at
Half an electron volt? Baloney. I'm sorry, that's 5,000 Kelvin. No way. No. Sorry. Rethink your energy scale, or maybe you were thinking in MEV, as in millielectron volts. So generally speaking, ytterbium will have CEF splitting modulo some hundreds of Kelvin, which is tens of millielectron volts.
No, you're right. I was thinking about this. Never mind. I was thinking about your 3 class versus 2 class.
Oh, no,
that's different.
Yeah. Yes.
You mentioned you can't clean these.
Ha.
Rockets.
Yeah.
Do they grow clean enough for oscillation?
Yes, we've done some of them. Yeah. All right, let me carry on. So go back to our questions, okay? If a crystalline cell gets larger and larger, does it start acting like a quasi-crystal? No. Now, you can say this is still pretty pathetic. It was only 14 angstroms on the side. If you want to get fully occupied crystalline unit cells getting bigger and bigger with rare earths or with magnetism, it starts getting hard. Okay? Second question, can a dilute ordered condo lattice be found? Absolutely, 1 out of 23. Does it act like a single ion condo? Absolutely not. Now, again, I have a rare earth at distance of only 6 angstroms. To get really larger, I have to start getting truly obscenely large unit cells. But at this limit, which is sort of pushing what we can do, we still have beautiful coherent behavior. Okay? All right. So these offered a beautiful playground for 3D and 4F examples of strongly correlated electron systems. And it really was an example of just do it. I had some crazy ideas that brought me to look at dilute moment-bearing systems, and this is what we found. So it was sort of fun. All right. Third, negotiation. Let's say that we're going to be interested in superconductivity. Okay, here are the generic phase diagrams, for example, for copper-based and iron-based superconductivity. And basically, we can see our dome of superconductivity is close to where we're suppressing some sort of antiferromagnetic ordering. So instead of saying, I want to find a high TC superconductor, that's hard to be actionable. Okay. If I say, well, high TC superconductivity is found next to suppressed and what I would call fragile magnetism, meaning as I suppress T-Nil, I'm suppressing the size of the ordered moment, then maybe I have a route of finding something interesting. Okay, so can I find other examples of fragile magnetic systems? Okay, so we can go about this in a variety of ways. Okay, we can study known, poorly examined small moment systems, and that was the case for lanthanum, chromium, germanium-3 a number of years ago. Okay, this is a material that orders ferromagnetically. We can suppress the ferromagnetism by diluting with vanadium up to a certain extent, but we can also, in the pure material, apply pressure. And we can see a suppression of the antiferromagnetic ordering, but then we end up at a tricritical point. This becomes first order, and we have avoided quantum criticality in a ferromagnet, which is predicted for most well-ordered metallic materials. So that was sad. Okay, well, then what we can try to do is look at poorly examined antiferromagnets. Lanthanum-2 nickel-7 has been known for decades, and it was suspected to have very small antiferromagnetic ordering, but the number of transitions, the position of the transitions were unknown, and it was only studied in polycrystalline form. We had to correct the binary phase diagram, but once we did that, we could grow beautiful single crystals. We could map out an anisotropic HT phase diagram where we see 1, 2, 3 zero field transitions. We could do neutron scattering, and what absolutely impresses me, this is a tiny ordered moment, but with a large single crystal, we're able to find all three orderings and understand their wave vectors. And we started applying pressure. Now, we were doing measurements in the basal plane, and for that, we could see that we have very little pressure dependence. The two sets of data are showing that there's actually a larger field dependence than a pressure dependence, but this was only up to 2 GPa. We are currently measuring in diamond anvil cells with the current along the z-axis where we see better features, and we're starting to map out what happens there. So this one's still in play. We can also just try to discover our own new small moment systems. Lanthanum-5, cobalt-2, germanium-3 is a crystal structure we discovered. It would be a nightmare with a moment-bearing rare earth because there are multiple rare earth sites, but with a silent 4F shell with lanthanum, we can just study what's going on with the cobalt, and we find a beautiful example of tiny, again, 0.1 Bohr magneton, itinerant ferromagnetism at 3.8 Kelvin. And what's lovely is it shows up in the specific heat. It shows up beautifully in the resistivity. We can see the ferromagnetism here. Unfortunately, when we apply pressure, we see yet another, by the way, new state is antiferromagnetic. We see another very clear example of the avoided quantum criticality. And Peng-Cheng, there's doping work on this now too, where we're mapping it with doping as well. That's Atri Das recently published. So those are one-offs. The question is, can we try to find examples of this en masse, sort of mass-produced rather than doing this artisanal work? And what I want to go over then is a way of trying to find this in systems that show collapsed tetragonal phases. Now, this is the thorium, chromium 2, silicon 2 structure. This is calcium, iron 2, arsenic 2. And what I want to show you is here's calcium. Remarkably, I'm going to be ignoring the iron here. Okay. Here's calcium, here's arsenic. At ambient pressure, I do not have bonding across this calcium layer, but with very modest pressures, oh, I get bonding. I go from an 11 angstrom to a 10 angstrom unit cell, and I also lose all magnetism. Okay, so this is something that we found in calcium iron 2 arsenic 2 when we discovered the material, applied pressure, but this is a type of transition that Hoffman was well aware of in the thorium, chromium 2, silicon 2 materials in some of the germanides and silicides as well as phosphides. Now, you can perhaps see more dramatically here in doped calcium iron 2 arsenic 2 with a little cobalt. We can again see that CT kills antiferromagnetisms, kills superconductivity, in the calcium, potassium, iron 4, arsenic 4, a quaternary superconductor, we can see our superconductivity. And when we hit a half collapsed tetragonal, we lose all superconductivity and magnetism. The point being, if you have collapsed tetragonal transitions, you often have interesting physics on one side or the other, and it gives you a well-defined tunability. So, can we look for other examples of this? We can look at the AT2P2 families. Yes, sir.
Can you explain what you mean by collapsed tetragonal? Is it just a volume change or a parameter change, or is it structural change? What's collapsing?
Again, if I had ready access to backup slides, I could show you explicitly, but what you have here is a tetragonal crystal structure. It remains the same tetragonal crystal structure, but all of a sudden your PP distance decreases or your C unit cell decreases. What's really nice is it's isostructural, okay? And that has profound implications. The talk I'll give in Karlsruhe next week is all about collapsed TAT, okay? But you can actually, you can fib nanocolumns and you can get 17 to 20% recoverable elasticity. And you can cycle these 10,000 times. So it's just gorgeous because I'm not having multiple phases, etc. So it's being looked at as a super elastic material.
What's causing it's a change of valence, or
It's a depopulation of the anti-bonding band, if you want to think of it. Now, that's a physics statement. A chemistry statement is, look, as I apply pressure, okay, I'm squeezing it, and at a certain point, all of a sudden, I start to get a little overlap between these, and you go, oh, we want to bond. And all of a sudden, they bond. So this is basically tuning in the solid state a bonding and anti-bonding of these pairs of atoms, or these planes. Yes, Paul?
That was hydrostatic or uniaxial with different directions, the pressure?
This is hydrostatic.
Okay.
When we fib a little column and then apply, that's uniaxial. You can appreciate uniaxial is more efficient. Yeah. Someone else had a question. Peng Cheng?
No, yeah,
Yeah.
basically saying, yeah, basically the moment collapses.
Now, when that happens, so you can imagine when I'm changing the bonding, when I'm depopulating this anti-bonding orbital, I'm changing the banding. And with a dramatic change in the bands, of course, stuff changes. Now, you don't know a priori whether you'll go from magnetic to non-magnetic, non-magnetic to magnetic, or nothing. But it gives you large tunability. So I can look at the AT2P2 materials. I can look at the barium examples, and all of these have PP distances that are in the unbonded. If I look at the calcium, all of these have PP distances more consistent with bonding. Okay. And by the way, for those of you who like looking at crystallographic tables, okay, you have to be super careful here. You have to make sure this is based on X-ray data where the whole unit cell, the whole basis was determined. Sometimes they will assign parameters based on unit cell dimensions, but they haven't done basis. The problem here is the phosphorus or the arsenic have a non-symmetry defined dimension. So you have to make sure of the purity of your data if you make a plot like this. The ones that are missing data have been measured for unit cell size, but they haven't figured out the basis. Okay. A comment for experts, perhaps. All right. And if we look at strontium, we can see that strontium straddles. So strontium looks promising. And as a matter of fact, the strontium nickel 2 phosphorus 2 is really right on the edge. So what we did was we could say, whereas neither strontium nickel 2 phosphorus 2 nor strontium cobalt 2 phosphorus 2 are moment bearing. They're not magnetic. On the other hand, if we dope in between them, we can see that as we get beyond about 50% cobalt, we can stabilize small moment antiferromagnetism. It rises, it falls, it changes to small moment ferromagnetism, and just before we get to cobalt, it becomes non-magnetic again. By the way, we did apply pressure to cobalt. We can see beautiful magnetism. That's not part of this. Okay, Now, what's beautiful is this follows Deguchi-Takahashi behavior. We can do mu effective over mu sat versus the temperatures. It scales gorgeously. We can look at the effective moment or the saturated moment, and they are tiny. So what we're doing now is we're looking and seeing if we can find quantum critical points on this side, either with the doping or by applying pressure to some of the ordered ones. And we've already studied the magnetism on this side. So this is a way of generating large numbers of fragile antiferromagnets or ferromagnets. And there are a lot of other members of 122 you can play with. In addition, we're generalizing collapsed tetragonal to other structures as well. Rosa Valente in Frankfurt and I have been collaborating for over a decade, and we have machinery for actually predicting these in silica now. And unlike many other predictions, these are actually quite accurate because this bond, not bond, is a huge energy scale and it's capturable. Peng-Cheng.
Yeah, so do you actually have critical behavior in terms of resistivity at 0.6 and 1?
We need to take it lower. At 1, it's not quite critical yet, but it's looking very close. So again, this is ongoing research. Yes, back there.
So it's really nice to have this bounding picture, but have you, like, how is it verified? It's only info from XRD or you have Raman stuff, Raman.
That's a good question. No, I don't have Raman. It's verified by X-ray diffraction, and the orbitals have been checked by ARPES. So you can see these orbitals that are identified as anti-bonding moving around as you go through this. Now, someone should call me out on my statement of ARPES, because a lot of this is under pressure and you can't do ARPES under pressure. Now, we've been able to finesse by annealing and playing around that we can get both uncollapsed and collapsed in the calcium, and we can look at that in ambient. Okay, internal strain aura. Okay, so lovely. Let me do a fourth negotiation then. Okay, and this is really more on materials design, and it's sort of playing off the quote from Einstein's objection that God doesn't play dice with the universe. Well, I think I'm playing dice with nature, and I want to shave the dice. Hey, if I can do it, I can do it. So let me show you two ways I consider of shaving the dice, and they're premised on these two very different binary phase diagrams. Okay, now,
Do the students understand what shading the dice is?
well, I was just going to ask, do the students understand what binary phase diagrams a little more? Well, shading the dice is illustrated here, Laura. Right. It's a way of cheating at craps or dice games. Look it up. I'm not going to teach you that. Right. Now, is anyone not familiar with how to read a binary phase diagram? Okay, good. Let's have a quick primer. All right. Temperature, composition, pure palladium, 70% sulfur. Okay. This is a single phase region. It's a liquid. Okay. If I cool down and hit this, I'm entering into a two-phase region. I'm starting to get a solid, in this case, solid palladium, and this defines the composition of the remaining liquid. If I'm here, instead of growing palladium, I'm growing palladium for sulfur. Okay. But again, when I hit this liquidous line, I'm going from a one phase to a two phase where the solid phase is read off to the side. Okay. Now, I like to do solution growth. Solution growth requires liquids. This is a remarkably low melting liquid of 625, considering that palladium melts above 1555 or 1550. Okay, so yay. All right, so do two different types of phase diagrams. Let's start with this one. Okay, so did I skip one? Yes, I did. So there are many examples of refractory, high melting transition metals on one side and volatile on the other. And this is really a mismatched desire. I want to make a compound that has high melting refractory and volatile and often toxic, may I add. That's hard to deal with. You try to arc melt it, and that's not very kind. You try to react it, it has difficulties. But what we've been finding over the years is you can find these eutectics on the transition metal side And as long as there's some compound on the other side, this is a valley of low vapor pressure because palladium doesn't have a large vapor pressure and palladium sulfur doesn't have a large vapor pressure, and sulfur is way over here. Okay, so we've been finding that we can create liquids that we can then drop other elements into and try to do ternary growth, or we can just access these binaries. Okay, good. So
Also,
yes,
very nice question. Actually, phase diagram you just showed, well, doesn't matter which one. If I wanted to vary the composition, I start from the lipidus and I just choose the different percentage of the initial material.
right.
That's
So
all.
if I wanted to grow palladium for some reason, I would put 10% sulfur, 90% palladium. If I want to grow this, I basically single phase liquid. This line here is defined by what I put in the crucible. Okay, so if I want to go over here, I put more sulfur in the crucible to start with. Absolutely. And we'll come back to that in a moment or two.
And you also use the word eutectic. Could you remind me?
Absolutely. Thank you. I assume all the students knew this, and this is just our theorist who doesn't know. Because if you didn't know what a eutectic was, you should have asked. Come on. No, I mean, this is a pedagogical thing. Don't hesitate. All right. So a eutectic this is the eutectic point. It's the minimum in the liquid where I have liquid coexisting with two different solids. Okay, for me, it's important because it defines, what the lowest temperature I can take this and still have a liquid. Okay, this, by the way, is a paratectic, a decomposition of a material, just another term. All right. So in that case, then, what we've been doing is we've been first making sure we own the eutectic. And we do that by putting our elements into the base of one of these fritted crucibles, heating it up, making sure nothing explodes, cooling it down, spinning right above the eutectic temperature, making sure the phase diagram is correct. And if we can do that without any evaporation, without any evidence of high pressure, without any bad things, we consider ourselves owning this eutectic, owning this region, and we can then try to do growth. Okay, so let me show you some examples. Okay, here we have the palladium, phosphorus, platinum, phosphorus binaries. You have two eutectics on either side of either immiscibility or this a series of compounds, and we've been able to demonstrate we can work with these. The reason I'm drawing this dashed line at 1,200 is you seal these in amorphous silica tubes. Amorphous silica is only good up to 1,200. Okay, so that's just an experimental reality. All right, so platinum has a large Z, but a lower density of states. Palladium has a smaller Z, but a larger density of states in elemental form. Okay, but it's something to keep in mind. So by adding various transition metals as well as aluminum, gallium, indium, we've discovered new X platinum 5 phosphorus, X palladium 5 phosphorus, and also grown the first single crystals of some of the known ones. Let me show you what you can do with it. Okay, so we were able to find high temperature ferromagnetism in chromium, platinum 5 phosphorus. There's a small site disorder between the chromium and platinum, but we were able to parameterize it. And what's remarkable, chromium is the only moment-bearing element here. It's 1 out of 7. Okay, this is ferromagnetic just below 500 Kelvin. Okay, and as a matter of fact, what's even more remarkable is the anisotropy field between H parallel and perpendicular to C is huge. At room temperature, it's still 20 Tesla. Now, this is fantastic because you usually associate this with rare earths or other such things. This is very nice as a demonstration. If you have large spin orbit coupling, you can have large anisotropies in a S or in a transition metal like material. Okay, now, on the other hand, before you get too excited, there is, of course, no hope of this being a practical magnet because it's almost all platinum. Now, Cab Calloway sang about a diamond car with platinum wheels in Minnie the Moocher. This is one that would have platinum magnet. But it's beautiful proof of principle that if you have large Z, if you have large Z with transition metals, you have the possibility of getting large magnetic anisotropies, and we might be able to finesse around the need for rare earths. Okay. Now, another example, we can have the manganese, platinum, palladium 5-phosphorus. It's isovalent and isostructural tuning of this manganese sublattice. And if you look at this scale, it looks like a boring ferromagnet the whole way. But if you look closely at the very, very small amounts of adding palladium, you see that the pure platinum is antiferromagnetic, and it takes homeopathic amounts of the palladium to get rid of this antiferromagnetism. And we actually have re-entrant ferromagnetism for some of these dopings. And we've been able to find that this host material, manganese, platinum 5-phosphorus, you can find it in other types of dopings as well. So interesting for looking at the magnetic ordering of the manganese there. All right, let me look at the other phase diagram, okay? Now remember, this is a single phase liquid. I'm not seeing a lot of single phase liquid. I've got a little bit here, I've got a little bit here, and a huge dome of immiscibility, okay? Immiscibility is oil and water. They don't want to mix, okay? And this is actually not as rare in binary phase diagrams as you may think. You have a lot of binary phase diagrams that manifest this immiscibility. And basically, these are all very similar phase diagrams. It's just a question of the temperature scale at which the top of this dome may exist. Okay, so for many years, these were turn the page. This is inauspicious. I want to grow out of a liquid. There's no liquid. Not good for me. And then I realized that was a prejudice that was missing an important insight. I finally got to the point of asking myself, okay, lanthanum and titanium, lead and cobalt, they don't like to mix. Can I find a ternary compound that forms? Okay, and remarkably, this is a question that had not really been asked. Okay, so what I found is there are relatively few ternary intermetallics associated with such immiscible or antagonistic pairs, but when they do form, you end up with the third element coming in as a NATO peacekeeper, separating them. Okay, so let me show you some examples. Here you have the lanthanum titanium binary phase diagram. There are very few, I think these are the two known ternary compounds. Lanthanum titanium germanium has the germanium separating titanium into sheets, lanthanum into slabs, a two-dimensional motif. Okay, lanthanum 3 antimony 5 titanium, the antimony sheathes the titanium into one-dimensional chains. Okay, so this is by segregating these unhappy pairs, you actually have a recipe for creating low-dimensional structures. And what's remarkable to me is the fact that they don't want to mix in the liquid translates into the solid of them not wanting to be next to each other. Okay, so we could look at another example. Here's the cobalt-lead binary phase diagram, highly immiscible. And by the way, most of these phase diagrams don't have any reported ternary compounds. These are just the ones I could find a few of. Excuse me.
Question.
Yes.
What physics determines when you have immiscible elements? Do you have a rough idea?
No, because it still is very poorly understood. And what I'm hoping is that people will come back. There have been empirical attempts by chemists and some physicists to try to describe it. I thought this was the perfect exercise for AI and ML, because everything is known about every element, including its taste, because old school chemists love to lick things. And I'm not making this up. Okay, no, it was hardcore. Okay, beryllium. Again, you think I'm making this up? You're wrong. Okay, but everything is known about elements. Okay, now you can make a vector of everything known about an element, and then you can take the binary phase diagrams and categorize them. Highly immiscible, highly miscible. There's some in-between ones. And I would think AI and ML would do it. I've actually worked with some experts and it pukes. It's still not getting it. So this is an active question, Piers. And I would love it because for me, what's remarkable, I always thought crystals had their own rules. You know, the bonding settled old scores and arguments, but in intermetallics, which have more flexible bonding rules, you can find some oxides with very rigid bonding angles that you can make and violate this antagonistic pair rule. But intermetallics, it holds every time I find a new material, and I'll keep going on it. But immiscibility is not well understood yet. And I would love it if it was. Okay, so let's look at this example. Did Piers get one already?
Sorry.
I'm looking out for you, Piers. Oh, yes.
So about the lanthanum and titanium stuff then.
Sure.
Is there no like,
Ask a question.
is there not like the perovskite material like lanthanum and titanium?
I just said oxides violate this rule because oxides have very rigid bond angle rules. And that seems to be an energy scale that trumps this. Okay. All right. So let's look at this. The only known compounds were these three. You have cobalt-6, lanthanum-12, lead. You end up with zero-dimensional lead being encapsulated by the lanthanum. You have cobalt lanthanum-5 lead, where you have 1D cobalt being sheathed by the lanthanum. And you have cobalt-13 lanthanum-6 lead, where you have two-dimensional lead and dense two-dimensional slabs of cobalt separated by the lanthanum. 0, 1, 2-dimensional motifs. You're dialing it in. We've been trying to have some control of dimensionality. This is at least offering it to you. And what we decided to do is, since we had proof of principle, we could stabilize some lanthanum, lead, cobalt materials. We asked ourselves the question, can we find others? So we looked in this region. Okay. And indeed, we found a completely new structure, a completely new set of materials, cobalt-4, lanthanum-4, lead. Okay. And what's beautiful is we have these distorted Kagame-like layers of cobalt separated from the lead by the lanthanum. Again, a two-dimensional motif. Okay. And what's even nicer is they're moment bearing. Not surprising. I've packed my cobalt densely enough and it's two-dimensional. I can actually get some magnetism here. And the magnetism looks like it has hints of two-dimensional order associated with it. And it's not just one material. We could find it for lead, bismuth, antimony. We have indications of tin. And they're all moment bearing. And they show, again, hints of low-dimensional magnetic ordering. So this is a beautiful recipe for dialing in dimensionality. And we've continued to look at this. We've found at least 4 other examples of new crystal structures that are antagonistic pair based and have low dimensional motifs. So this is very, very intriguing. And as a connoisseur of binary phase diagrams, it's nice to see these phase diagrams that in the old days turned the page, nothing here, turned into, whoa, that's an opportunity. Maybe I can create a new low dimensional material for study. Okay. All right. So up to this point, I hope I've convinced you solution growth is versatile for discovery of new materials. Over the past decade or so, my group has really been advancing it, trying to make it more versatile and more quantitative. So in this last part, I want to go over how using these fritted crucible sets has allowed us to make binary phase diagram determination, reuse of decanted material, removal of nucleation sites, fractionation, and creation of saturated solutions. So now we're going to go a little bit more into the details of crystal growth. Okay. Let me make one point here. When we came up with this design, I worked with LSP Ceramics. I do not have any intellectual property on it. I basically work in collaboration with them. I get 0 pennies on the dollar for these. I just get the naming. Okay. But these have been very, very good. At this point, 300 labs, 30 countries, 6 continents. I'm waiting for Antarctica, but they're actually being used a lot by many of my colleagues. Okay. So if you do use them, the only way I keep score is refer to the paper. Give us a citation. All right. So let me start with this. In 2013, we discovered a whole family of binary rare earth bearing quasicrystals. They were spin glasses, yay. But to do this, we needed to redetermine the cadmium rare earth binary phase diagram. These were the new points that we had to do because this phase was not known. It was just thought that this went all the way down for the approximate GAD-OCAD6. So how were we able to do this? Well, solution growth is premised on interacting with this line, and it can actually be the arbiter of where it is. So this is going back to the question of how do I control? Oh, Alex is gone. Okay. How do I control what my growth is? By putting elements into the crucible. So if I know the initial mass and composition of the melt, and I'm better, and I can measure the mass of a single phase grown or the mass of decanted liquid of a single phase grown, I can put a data point on the liquidus line. So let's have a growth. I don't know where this liquidus line is. I don't know where I'm hitting, but if I hit and grow single phase GAD-OCAD6, when I decant, I can weigh how much GAD-OCAD6 I grew and subtract it from what I put in. And that gives me this composition, pink. Okay. I can cool to lower temperatures and put other data points on. If I cross a paratectic, start growing another phase, it's more convenient to come in with a composition that, again, I grow a single phase. If I know this composition, I can put another data point on. So we can determine phase diagrams. We can correct phase diagrams. This is useful. Okay. Now, in addition, if you work with neutron scatterers, they have very expensive habits. Okay. First of all, they always do this. You know.
What does it mean?
Exactly. How big is the sample? Oh, the size of my
Oh, I
thumb.
see.
This led to an idiom in our group. We want to work with scatterers who have small thumbs. Now, every now and then we grow a crystal that's so big, okay, that the scatterer says, oh, I'm going to have to cut it to fit it in. And then we give ourselves a John Holmes Award. If you don't understand it, look it up. Okay, fine. So for these materials, cadmium is quite an absorber. So, whoops, excuse me, back, no, forward. Cadmium is quite an absorber, so we have to use cadmium-112, which is an isotope that you buy by the milligram.
Very expensive.
By the milligram. So I was doing this with Alan Goldman. We wanted to look not at the gadolinium, but the terbium. Okay. So if you come in here, you're basically 99% cadmium. You grow a little of this, you throw all that cadmium out. That's bad. With these treated crucibles, you're keeping your decant clean. Okay. In the old days, you decant into silica or fiberfrax, and it's just a mess and you contaminate it. Now you can keep it clean. So what we can do is we can do this multiple times. We figure out how much of this we grew. We know that the composition of the decant, we can add it in again and again and again. And when we're all done, we can say, look, we can compare to the crystalline approximate, put in a lot more gadolinium and grow it out. And that way we're not wasting very expensive material. We do the same thing with platinum and palladium growths, although they are cheap compared to this. Okay. Now, the word fractionate is generally associated with the petroleum industry, where they're evaporating off different fractions of hydrocarbons. Okay, but you can fractionate a liquid as well. And we've found that this is what's enabled us to get large crystals of these rare earth palladium-3 sulfur-4, or let us optimize any growth that we look at. So let me explain what the problem was. We could own this palladium sulfur eutectic, we could work in it, and one of the first things we wanted to do is see if we could grow some of these rare earth palladium sulfur-4 materials. The cerium's interesting, the europium's interesting, we did a lot of fun work on them. But when we first put in a little cerium here, we got the right phase, but the right phase was barely visible to the bare eye, and we got a lot of this binary cerium sulfide, palladium sulfide, oxysulfide stuff that we called crunchy critters. It's what we didn't want. Okay. So how do we improve? Well, we can fractionate. And what I mean by that is we can take our initial composition heat it up to 1150, stay there, and see if we even are in a single phase liquid regime. We were not. Okay, so we got rid of this, and then we reused the decant. We heated up a little more, 1175, cooled down to 1050, still had this wrong binary phase. Get rid of that, reuse the decant. Now we heat up to 1075. You'll note that I'm heating up to a little above the decant, but each time I cool lower. Now to 1000, right phase. Reuse the decant. 1025, 950, right phase. Reuse the decant. 975 to 900, right phase. Reuse the decant. 925 to 670, wrong phases. So we were able to identify the key temperature region where we're interfacing with the liquidous surface for these materials. Okay, so what we could do then is we could come up with a two-step process. The first step, 1150 to 1050, gets rid of these unwanted binary phases, and more importantly, gets rid of any oxysulfides. Yes?
Do you switch between the temperatures very quickly, or do you let it cool, come back later, go again?
So we heat up, go to 1175, dwell there for 8 hours, 36 hours down, decant. Now, in reality, when we've been doing it even quicker, I get in early in the morning. So I get in at about 6:30 a.m., not p.m. So I decant, have my coffee, come back, open it up, see what there is, reseal, put it back in the oven. It's in the oven by 8. Okay, I can heat up, I can cool down, and repeat the next morning. So in a week's time, we can go through steps like this and identify the region we're interested in. And once we've identified it, we can then do much slower coolings. So now that I've identified the right region, I get rid of nucleation sites and I slow cool over the magic region. And I've gone from things that are tiny submillimeters to things that are almost getting into centimeter sized, which is lovely. Did I answer your question?
I was wondering how you control the process.
Well, I have a furnace that has a temperature controller and it talks to this magical device called a computer. And I have told the computer, well, you have to understand, when I first started doing this, the magical device called a computer wasn't there. You still had these clockwork mechanisms that had claws on a variac, and it was turning down the amount of current that you're putting through. So this magical device called a computer is a lovely thing. I'm sure you've heard of them, even here. Did he get a crucible? Yes. Oh, thank you.
Maybe the question was, you centrifuge at a high temperature.
No, he didn't ask anything about decanting. Did you?
For 10 minutes.
I'm almost there.
But
What-
you do centrifuge at a high temperature.
No. Well, again, the centrifuge is at room temperature.
Yeah.
Right. So the process at, yes, so the process, and I have a video I can show you afterwards. The process is at 900, okay? I have a mask, I have gloves, I have tongs, open it up, take it out, put it in the centrifuge, close, hit the button. So about 5 seconds and it decants. The centrifuge is not hot, it's a dynamic process. If I open the oven, take it out, have a Giton or rosé, and then decant, then I'm sad. Well, there are different systems.
But it's quite a loss of temperature.
No, absolutely not. No, I have gone within 10 degrees of a eutectic and still decanted. Let me finish up and then we'll come back to this, okay? All right, yeehaw. So, final example. So Piers gave me a 10-minute warning. I'm almost there. Let me give you a final example. And this is one that, again, I want to illustrate how stupid I am because it took me a long time to figure this out. So, rhenium-3 germanium-7 was found to be a metal insulator-like transition by a former student of mine, Udok Moon, who's now at Simon Fraser. You have a beautiful feature in the resistance. You have a loss of polyparamagnetism in the susceptibility. I wanted to grow these to apply pressure. Okay, lovely. So here's the phase diagram. And unfortunately, this is an inauspicious phase diagram because this is virtually a vertical line. So if you're going to want to say, I want to hit this liquidus, it's really hit or miss. Okay, so how the heck am I going to do it? You can try here and here and here, and maybe, oh no, that doesn't work that way. It's not friendly. Now, in addition, phase diagrams are suggestions of reality, so this exact number probably isn't known. On the other hand, the paratectic decomposition temperatures are generally much more reliable. Okay, so what I realized is I was doing this a stupid way. What I could do is put in way too much rhenium, and I made sure it was a solid ball, not powder. Okay, and I heat it up to 12, sit there a long time, and cool to just below this purported paratectic, and decant. I still have most of my rhenium ball undissolved, but I decanted a perfectly saturated solution. Nature's giving it to me. I don't even need to know exactly what it is. I just need to put in too much and decant. So with this two-step process, every single time I could just get beautiful single crystals of this rhenium-3 germanium-7. We could actually look at it. We could suppress our metal insulator, a density wave, and as sort of as many people's prejudice, we could see a nice superconductivity next to the structural density wave like transition.
Why does it grow so thin needles like structures?
Well, generally it has to do with the geometry of the unit cell. So often the manifestation of your crystal has the inverse ratio of what you'd expect the unit cell to be. Okay, so it's an anisotropic unit cell.
Cell is so anisotropic.
Yeah.
It's very, very bad.
Well, I mean, look, this is nothing compared to niobium triselenide, which you can yank out a hair, and that's a big niobium triselenide crystal. Yeah. So, all right. To summarize and to make peers less anxious, a flexible mapping of the periodic table combined with ideas and motivations, rationalizations, good, bad, stupid, smart, is going to keep populating quantum materials. So I would maintain the future is growth, the future is strong, and just do it. So with that, I want to thank DOE and BS. They have been funding this for a goodly number of decades, and this is the funding that allows us to have long-term projects and long-term agendas. And a lot of this is summarized in this Reports in Progress of Physics article, New Materials Physics. The first half teaches you how to grow. The second half teaches you how to have ideas. And let me go past the jokes. If you want, no, that's not what I wanted. How do I stop this?
Escape.
I want to go to the next one. There. So how do I get this to work? Because what I wanted to do was to, how do I play this?
Good question, but yeah.
Not my computer.
Well,
Yeah.
not my software. I don't use PowerPoint on any occasion, but let's see. Let's see. We need to get the cursor over there, probably. We can be so lucky to manage to do that. Let's see. No, drop the thing down. No.
All right, I just wanted to show you, there's a film, there's a science show in the US called Nova, and I taught the guy in it. Yeah, maybe you can do it this way. Just go on the PowerPoint. There, hit the arrow. Super. Cannot play media.
Okay. Interesting.
Okay, it worked on my computer, but forget about it. It was just basically showing you the decanting process. Questions in the remaining time?
Okay. I have a lot of questions.
That's it?
So.
Yes.
You have deep experience from many, many years of crystal growth, and the periodic table is vast. So what are the sensible strategies for navigating, for making maps and telling us which way to sail?
Well, let's have a negotiation right now. What physics are you interested in? because that's the first step.
Yes.
You know, if you're interested in fragile magnetism, it's one thing. If you're interested in metal insulator transitions, it might be another. If you're interested in low dimensionality, if you're interested in singlet ground state materials, I mean,
What about if I'm interested in things that haven't been discovered yet?
well, things is a rather vague term.
I
again,
know,
Pierce.
but like
So-
discovering the continent of America wasn't. Okay.
All right, so
Maybe.
I get
that. Make
right.
that dis-
So I would say this, the
Can actually this.
no, let me go here. Right, so I lost my laser pointer. Oh, there, thank you. So my group has three motivations, and this is going to get to it. So sometimes we want a specific compound. At a certain point, we wanted MGB2. That's a specific compound we
Sure.
wanted to make. Okay, good. Sometimes we want a specific ground state. I would like to find a ytterbium-based condo lattice. I want to find a praseodymium system that goes heavy. I want to find a fragile magnet. Okay, and sometimes we want to search for known and unknown unknowns. And you're in the final end one of unknown unknowns.
Yes.
Okay, so I would say that the antagonistic pairs algorithm that I went through is a way of discovering new crystal structures, possibly with low dimensionality. But whenever you find a new material, you have to interview it. And that's the beauty of being an experimental physicist. You know, you interview nature, nature always answers, you know, so what's your crystal symmetry? Orthorhombic. Are you a superconductor? No. Are you a magnet? Yes. What's your resistivity? Weird. You know, and then you have to think. So
Yes.
you always have to interview the material to figure out what it is. So for your,
Oh, no, yes, I thought you were done.
yeah. So if you're really going for the unknown unknowns, look, I had a graduate student who brought in a blowgun. Okay, I got pretty good at it. Those three elements, let's see what we find. Now, that's a little facetious. Okay. On the other hand, we can say, look, I think that cobalt might be a promising system for fragile moments. Let me see what new cobalt compounds. But again, I'll dial some physics in. If you're just saying complete unknown, well, I generally have some prejudice I bring into what elements I put into the crucible for my growth. Now, it could be, look, no one, I don't see any ternaries between palladium, tellurium, and aluminum. And palladium and tellurium might give me layered correlated materials. The aluminum might stabilize. I'll look at the structure.
Okay.
So,
Laura.
Yeah, so instead of discovering America, discovering another, you know, another thing that you know what you want. So the big question is, no one could predictably design superconductor or thermoelectric. It's even hard to put Faraday rotation materials. So how would you go about getting a better thermoelectric?
I don't do thermoelectrics that much. I'm going to pass on thermoelectrics. On the other hand, let me go sideways like any good politician. Ambient pressure materials, especially binaries, synthesized at ambient pressure, have been pretty well explored. Okay, there's a whole other Riemann sheet, just a few GPa above. Okay, so one of the things that we're starting to do now is try to find metastable materials. We're synthesizing things at 3 or 6 GPa, which are pressures that often you can bring them back down, quench them, and have your new structures metastable. That's been poorly explored. So you can have the same luxury that Bernd Matthias did, where many superconductors had not been tested in binaries or whatever. If you just make them at high pressures, quench and see what's going on. So that's a terra incognita. Oh, that's a terra incognita that we're playing with,
Yes.
and we're starting to do now.
Yeah.
So that's sort of fun. And This is, of course, springing off of the incredible seminal discovery of Mikhail Eremets, where he was able to stabilize barn temperature superconductivity. It's not quite room temperature, but in Iowa, the barns get cold. So, well, no, I mean, about 260 Kelvin, I'm good with that. Those are the days you like having a beer. But those are made at 150, 200 GPa, and they're not recoverable. But there are a whole bunch of materials you can make. Diamond's metastable. It's pretty useful. And I think that's a very fertile hunting ground.
Yeah. Okay, let's give Paul a big hand.
All right.
Yeah,
Yeah,
we're going
thank
to
you.
start
Thank you
again in
for
20
room
minutes,
sharing.
5 to 11, 5 to 12.
Right. And you can just delete that.